Okay, let's begin. First, probably let me discuss some of the questions from the Midsem because I found a lot of probably confusions were there. So let's start with the first question. The first one was our very own defamed. So he had something like this, and yeah, I had some source follower in the second stage, but for the first part, I told you are supposed to find the short circuit GM and the output resistance looking here. So whatever you have here doesn't play a role. So I'll not consider this. So again, this was V1, V2. Let me quickly label them. So again, for short circuit GM, you are going to short the output and find the current here. And again, this is an asymmetric circuit, so all your half circuit concepts will not work. So you have to sit and solve. So what's the first thing you'll find here? You'll find this tail node Vx. And for this part, I told that you can assume the R0 of the NMOS is infinity. So if the R0 is infinity, what is the looking in impedance here? 1 by GM. I think that much everyone is fine. So again, looking from M1, this is the circuit. You have here some resistance Rs, which is 1 by GM. And M1 and M2 have the same GMs I told, so this is also 1 by GM. And this is ground. So what is this voltage then? Yeah, I mean, if this is a general RS, what is it? It will be GM on RS by 1 plus GM on RS times V1. And please remember, this is valid only if the when this is valid? When basically the drain resistance is much smaller. Okay, so this is again valid only if the R0 is much greater than the whatever resistance you have at the drain, and in this case it's valid. So this becomes V1 by 2, and so again we have done this multiple times. So this is V1 plus V2 by 2. So what is the current here? We call it I1. So this was GM 1 times V1 minus V2 by 2. So where will this I1 flow? It will go to the short circuit here, right? So what is my short circuit current? Minus I1 due to this, but this current also flows here. So what will happen because of that? That is again everyone is making a mistake here. See how a current mirror works. You should understand what is the cause and what is the effect. See, for current mirror, if you pump in a current in the branch where you have the diode connected voltage, that current is mirrored here, right? I mean, that works because the current here flows and generates the required gate voltage here, and that gate voltage in turn results in the current in the other branch, right? So it is not as though if you pump in a current in this branch, it will result in the same current here. Okay, so only this works. I mean, that's why you should clearly understand what is the cause and what is the effect, right? And even here it's pretty simple to see, right? What is the incremental gate voltage for the transistors M3 and M4? What is the incremental gate voltage? Yeah, short. What is the voltage then? 0. What about the source voltage for the transistors? That's also incrementally short. So there will be no incremental current at all due to these transistors. So this is something commonly found. Most of you told that this I1 current flows in M4 gets mirrored in M3. That doesn't happen, right? It's always the other way, right? I mean, current mirror works in this way. You have a current flowing in the branch where you have the diode connection. That current gets mirrored in the other branch, right? Not the other way around. So the final short circuit current is just minus I1, and that's basically minus So what's the short circuit GM? Minus GM1 by 2. Okay. I mean, this is also important. Some of you have got GM1 by 2 but missed the negative sign. Okay, so that's about the short circuit GM. Hopefully this is clear now. So next was the output resistance. So we'll erase these questions. So again, for output resistance, you will apply some test voltage here and find what is the test current here. So if this is the test voltage, what will be the incremental current here? We call it some I3. GM3 VT. That's fine. But the same test voltage is applied to the gate of the transistor M4 also. So what will be the incremental current in the transistor M4? Same 3. If you assume GM3, GM4 are equal, GM3 VT. So you have a current GM3 VT flowing in this transistor. I'll call it as I3. So what will be the current that will be flowing here? Huh? Sorry? Okay, again, so I mentioned in the class, but I assumed some conditions, so you should carefully work out. See, say where to draw the equivalent circuit for the transistor M4, I have these two. This current is your GM3 VT, right? And for simplicity, I'll assume the current is flowing in the opposite direction, and it will make it easy for you to appreciate things. So this is minus I3. Okay. Now I am supposed to find what is the current that is flowing here, right? Because this current is what will flow back like this. So this current minus I3. So I mean, if this current is minus I3, what will be the fraction of the current that will flow here? Huh? I mean, current division here, right? So basically, I mean, this current I3 can either flow into R04 of this transistor or flow into the impedance looking down, right? And it will be the current division between those two impedances. So what is the impedance looking down? If I call it some R down. I mean, okay, yeah, if assume R0 for all transistors now, what is it? If assume R0 for all transistors now. Huh? Yeah, I mean it's a cascode, right? So what is it? Yeah, I mean don't simplify, just tell the exact expression. Yeah. No, I mean it's R02, this transistor M2, plus the impedance looking here. What is the impedance looking here? 1 by GM, because this drain is short, right? So that is 1 by GM1 plus GM2 R02 times 1 by GM1, and the two GMs are equal, so this is as good as 2 R0, 1 R0 to something. Okay. So now tell me what is the fraction of the current that flows here. If I call it some I4, what is I4 in terms of I3? R04 by times I3. Is that okay? Is the current division between the two impedances. So what is the total test current I will have? This is the current, right? This is I3 and this is I4. So what is I3 minus I4? So you simplify it, what you will have? So you will have GM3 V test times 1 plus. Sorry? Yeah. Oh yeah, sorry. Yeah, right. Yeah, thanks. Yeah. Yeah. So I test is basically I3 minus I4. That's why you get the positive stuff finally, right? Yeah, thanks. It's I3 minus I4, right? So this is 2 R02, right? So what is the output resistance? or let's say I'll write the output conductance. What is it? Yeah, it's GM 3 times this factor, right? So I mean, in the class I told it's roughly 2 GM, and when will it be 2 GM3? Under what conditions will this become equal to 2 GM3? Huh? When R04 tends to infinity, it becomes 2 GM3, right? That is, when this impedance is infinity, then the entire current here will have to flow. In the class, that's what I told. I assume that if some R0s are infinity, then the entire current flows, and then you will have 1 by 2 GM. And if R0 for the transistor M2 is infinity, what will happen? This term basically goes to 0. The impedance looking here is still 1 by GM3. Okay. So again, in the class I will just give you some rough results under some special cases. I expected that you will guys work out completely. So this is equal to 2 GM3. Is that okay? Cool. Then the next part was to find the poles and zeros. Let me quickly do that. So we had the source pole over here. And for poles and zeros, I told to consider only the capacitors here, here and here. And I mean the poles due to these capacitors we derived in class multiple times, so I'm not repeating that. So the only additional thing is the pole due to this capacitor. And what will that be? If I call the capacitor is CL, and this is M5 and M6, what will be the pole due to this capacitor CL? The impedance looking here is what?
1 by GM parallel, 1 by GM.
Yeah, it's
R06.
yeah. If R06 are all infinity, it's basically 1 by GM5. So the pole is GM5 by CL. That's all, right? It was basically GM5 by CL. And of course, in the last part, I just told you have one more capacitor. I think, and that capacitor was the gate to source capacitance of M5. So one thing I found is a lot of you guys had considered it as a two-stage OTA, where you have a GM like this, and CC is put in feedback. C6 is put in feedback. I mean, this is fine. You consider it correctly, but I mean, in fact, I gave you as a practice problem question, right? For a source follower, you can actually model it as a two-stage OTA, but you should be careful about what is the GM and R0, right? So what will be the GM for this? Yeah, it is basically, yeah, I mean, it is a short circuit GM for this guy. Okay, and if you short circuit the output, the trans conductance is still the in GM of the transistor. So GM is fine. What is the R0? It's 1 by GM. Okay, that's also 1 by GM5. So this is something most of you had gotten it wrong. I mean, you consider this to be the output conductance R0 of the transistor, and things will go wrong, right? And another thing is, if you look carefully, the sign will be like this, right? Because it's connected between gate and the source. Between gate and the source, there is no sign inversion, right? The source is simply following the gate voltage. I mean, and you don't even have to do these things, right? So, what kind of a stage is this? It's a voltage buffer. Like, I'm applying voltage at the gate, taking the voltage output from the source. It's a source follower. And for convenience, I told that R0 of all the transistors are infinity. So if this is some, I don't know, V5, what will be this voltage?
V5.
That will also be V5, right? I mean, because if you draw the incremental equivalent for the transistor M5, you will have what drain is grounded. You will have GM5 of the transistor times VGS, and everything is open circuit. So that simply says What do you get because of that? If this is an open circuit, what will happen? This is the incremental equivalent, right? I am drawing the incremental equivalent for this guy. This is the GMVGS.
VGS should be 0.
Yeah, and all R naughts are 0. It's an open circuit, so the current value must be 0. So that simply says gate to source voltage is 0. So V5 will follow V6. Sorry, or the gate voltage will follow the other way around. Source voltage will follow the gate voltage exactly. So this is essentially the case like this, where you have a buffer, put a capacitor around it. So these two voltages are exactly the same. So what will happen?
No.
The capacitor doesn't play any role, right? It is connected between two equipotential points. So it doesn't draw any current. So it doesn't add any pole or any zero. Okay. Cool. So then let's move to second question. So second question was basically something like this, where you have an incorrect cascode. And this was M1, M2 probably. Again, the first part was to find the short circuit GM. This was the input. So again, one common thing I found was you guys wrote that the current in this transistor is GMVin. That is not correct, right? Remember, the current is GMVGS. It is not just GM times the gate voltage. So what is the impedance looking down? It's 1 by GM of the transistor M2, 1 by GM2. Now it's the same thing as your source follower. So you short circuit and find the short circuit current. I'll give the expression directly. It will be GM1 by GM, right? The same thing. Sorry, by GM. Yeah, this will be the current. I mean, this is basically of the form GM by 1 plus GMRS. I mean, if you remember in your first practice set, I gave multiple stages. One of the stages was this, and asked to find the short circuit.
I out.
Yeah. So that's fine. The output resistance, I think that most of you got it right almost. So output resistance has two components now, one looking up and one looking down. What is the impedance looking up?
R03 plus.
Yeah, it is R03 plus
1 by GM4 plus GM3
GM3 R03 by GM4. Again, plain cascode impedance. I mean, you can simplify this. R03 will be much higher than 1 by GM. So this you can approximate as R03 plus 1 by GM4. Now we'll have a similar expression for the impedance looking down, right? So the final output resistance is basically the parallel combination of these guys. That's all. Yeah. So another thing I wanted to say is, see, I found you guys found out R up, R down, but then some of you actually simplified the expression for the parallel combination of the resistors and stuff, and that's not needed, right? I mean, see, this is not a mathematical course, right? I'm not some sadistic mathematician who gets happiness in making you write some 2 lines of long equations. Okay. See, for a circuit designer, this makes no sense. For a mathematician, this looks very good, like a nice rational polynomial. But for a designer, what makes more sense is this, right? If you write R1 parallel R2, it gives you physical intuition of what is in the circuit. So if you don't need to simplify things, just keep it plain. It should be readable and understandable, that's all. Okay. Yeah, and the next part of the question was to again find the poles and zeros. Let me do that quickly. You had capacitors at the output. I think this was CL. I think this was C2. Probably this was C4. And I mentioned that CL is much greater than C2 and C4. So for estimating pole locations, you make the same assumption. Assume that the poles are uncoupled and they are far apart. So what will be the dominant pole? or which capacitor will contribute to the dominant pole? CL, right? I mean, simply because I told this is much larger, so it makes sense. This most likely will contribute to the dominant pole, and for that you just need to find the impedance looking into this capacitor. And when you do that, what will you do to these capacitors? Why do you open it?
Because they are required.
Huh? Yeah. Again, exactly. Right? What's a dominant pole? As you know, it's the lowest frequency pole in your system or in the circuit. So, and I already mentioned these capacitors are very small. A small capacitor at low frequencies as good as open. So we can open these. So the impedance looking into CL is the output resistance you computed before, and that gives the pole location, right? So that was R out times CL. That's all. So next we have two non-dominant poles. Let's say I find the non-dominant pole due to this cap. Again, I just need to find the impedance looking here. I have looking down, what is the impedance? 1 by Gm, straightforward. Now I just need to find the impedance which is looking up. And when I look up, what will I do to the other capacitors?
Oh, for sure. Not CL only. We can
Yeah, only CL you short. See, again, I found some of you guys had actually opened all the capacitors. Oops, should probably undo. What I found was some of you guys had opened the capacitors, and to find the looking up impedance, you included the cascode of the entire thing. That's not correct, right? Simply because now we are looking at non-dominant pole, and the assumption is the poles are very far apart. So the non-dominant pole is at a much higher frequency than your dominant pole. So by the time you encounter the non-dominant pole, yeah, the capacitor that contributes to the dominant pole will behave like a short, right? So this is now a short circuit for all practical purposes. You cannot say anything about C4, but one thing you can say for sure is CL is short. So if that is the case, now the impedance simplifies. So looking down, you have 1 by, let me write in different color maybe. So looking down, it was 1 by Gm2. Looking up, what is the impedance? 1 by Gm1, right? That's all. So the pole location is what? It's basically the sum of the two Gms by C2. So we'll have an identical case when you repeat the calculation for C4. Okay, cool. So let me move to the third question. I think third one was an easy scorer. Most of you got it right. So G2 C2, and this was 1 by Gm2 Cc. And I also mentioned that this OTA is driving a load conductance GL and the load capacitance CL. So first mistake I found was most of you guys didn't include GL and CL, right? That you'll have to do, because see, this is an OTA. The OTA does not have, the OTA has only the intrinsic conductance and capacitance. But finally, when you put it in unity feedback, it is driving some load. And to find the phase margin, you are going to break the loop somewhere. Oops. To find the phase margin, you are going to break the loop somewhere. So for the loop gain calculations, the load impedances will come into picture, right? So the second thing I found was, in fact, some of you asked during the exam also, the phase margin, some of you wrote it like this: minus tan inverse omega u by P2, and then you guys had a third term, Gm1 by Gm2, right? Should you have this term here? No, right? Because I clearly mentioned you have the zero cancelling resistor, right? So this shouldn't come. And if you included, I think you would got some negative capacitance or some weird values. Right? And I mean, in fact, some of you even copied the circuit wrong. You didn't even add the resistor when you draw it on your paper. I mean, so be careful.
There was third pole into
You'll have a third pole, yeah, but that can be neglected, right? That's very at a much higher frequency. Yeah. Yeah, so this is the phase margin roughly. And the other part I wanted to discuss is, yeah, here the second part of the question was what will happen to the phase margin if I go and reduce the intrinsic conductances. So first, can you tell me what is the unity gain frequency here? What is it? Omega u?
GM1 by CC.
GM1 by CC. What is the first pole location? G1 by roughly CC times GM2 by I'll call GL prime. Again, GL prime I'll say it's GL plus G2. CL prime is CL plus C2. That's all. And what about the second pole location? GM2. Okay, if you write it exactly, it is GM2 into CC by something. That factor is almost 1. Plus I'll have GL by CL prime. Okay. So if I mean, the phase margin depends on what? From this expression? Depends on omega e and P2. That's all. So if I reduce G1 and G2, what will happen to omega u? No change. What will happen to P2? No? Yeah, I mean, see, again, this is something I found. Strictly speaking, mathematically, P2 is reducing. No, I mean, no doubts. But yeah, the point is, how much is it decreasing, right? GM2 is much higher than G2 and GL. In fact, that's what you want, right? You want the second stage to have some gain. So you want GM2 by G2 plus GL to be much greater than 1, right? So for all practical purpose, this is what? How can I approximate it further? It's GM2 by CL prime. Okay. So some responses I found was, if you reduce G2, the second pole reduces, so the phase margin degrades. I mean, mathematically speaking, it might be fine, but practically speaking, that contribution is negligible, right? Because GM2 is dominating it so much, the reduction in P2 will be by 0.01% or something. That's literally nothing. Okay. So another couple of responses I found was, if you that I'm coming to that. If you reduce G1, P1 is also going to reduce, so the phase margin will improve. But again, for P1 is already at a much lower frequency, that the phase it contributes is almost 90 degree, isn't it? So even if P1 reduces, it's okay. It will give the 90 degree phase at a much earlier frequency. At omega u, it's still 90, right? Again, mathematically speaking, that is also correct. So actually, it will not be 90 degree; it will be 89.89 degree. If it reduces, it will become 89.899 degrees. That's okay. So again, note that this is not a strictly mathematical course. You just need to know in practice, when you design, what will happen. You just need to have that physical feeling and intuition of what's happening in the circuit, right? So if with that understanding, what will happen now if I reduce G1 and G2? Phase margin will not change. Even if it changes, it will be like insignificant. Okay.
So why don't we use this technique?
Yeah, I mean, we do that, right? I mean, the point is, how do you decrease G1 and G2? That's all. I mean, it's easy to write on paper, I'm reducing G1 and G2, right? So how do you reduce G1 and G2? Do you know some techniques?
Increasing R out.
Yeah, you just have to increase R out. You do cascoding, folder cascode, whatever. So again, in this question, I also asked you to sketch the Bode plot. I mean, and reason I asked to sketch was, I asked you to sketch the Bode plot before and after decreasing the conductance. And usually the reason I asked you to do is so that you know how the plots look like. And usually if you want to compare two cases, you plot them on the same graph. I should have probably mentioned explicitly, but you guys plotted in two separate graphs, right? So that will not give you the feel for what's happening. So let's quickly sketch it on the same graph. So let's say initially you have something like this. This is omega u. I have P2 and P3 comes later. I'll ignore that. So the phase is doing this and then probably does something. Now this is my earlier P1. Now if I reduce G1 and G2, what will change? P1 is changing, omega u is still the same. And at omega u, the slope is rising by the same 20 dB per decade. So it will rise like this. And let's say here is your first pole. Yeah, assume it's a straight line. So this is your new first pole, the higher DC gain. And the phase will probably do this. It will attain 90 degree quickly, but again it will follow this. Okay. Cool. So then only one question I wanted to discuss. Yeah, I think the fourth question was what? Yeah, in the fourth question, what we did was this. So instead of doing Miller compensation, let's say you add a capacitor here Cm, which is basically your Cc times Gm2 by G2, GL prime. So what will happen, right? So if I do this, what will happen to omega u? Or first let me start from the first state. What is the DC gain? Same as before, right? Gm1 by G1, Gm2 by GL prime. What is the first pole location?
Same.
It is same. So G1 by roughly Cm, that is Cc times Gm2 by GL prime. So what will happen to second pole location now?
It will be now GL and
GL prime by CL prime.
CL prime.
But before, what was it?
Was GM2 upon CL.
CL prime. Right? And so if I do that, what will happen to the phase margin now? I mean, basically with Miller compensation, this was P1, this was P2. If I don't do Miller compensation, and instead if I put this large capacitor at the first node, this is the second pole here. This is at a lower frequency or a higher frequency than this?
Does it depend on the values?
It depends, but you know, right? GM2 and GL prime.
But
It's GM2 and GL prime, right? GM2 is much greater than GL prime, right? This is, I mean, again, you want the DC gain of the stage to be higher, so GL2 by GL prime to be greater than 1. So if I do this, what will happen to the second pole? Is it increasing or decreasing? It is actually coming to a low frequency. So what can you comment about the phase margin? It will decrease. Omega u is still the same as before, right? I didn't write omega u. Omega u is basically product of the two. That will be again at the same frequency. Omega u is still same as the Miller compensation case, but the second pole now has come to a lower frequency, so the phase margin will actually degrade. And in fact, this technique is called dominant pole compensation. Where the idea is you go and put a large capacitor at some node to make that particular pole dominant, and the hope is that since that is a dominant pole, the system behaves more or less like a first order system. But the deal is, if you do Miller compensation, you get double Monty, you get pole splitting, wherein you not only have one pole moving to a low frequency, the other pole shifts to a higher frequency.
But in this we have feed forward.
But you can cancel that RSP zeros, right? But when you do the dominant pole compensation, only this happens. The second pole remains at the same location. So the phase margin is not so great. So the bottom line is, if you have to get the same phase margin as the Miller compensation, the cap you have to put here will be much higher. Basically, this pole has to move to a much lower frequency so that omega u reduces a lot, and then the phase margin could be same as your Miller case. Is that okay? Okay, the fifth question I'll discuss tomorrow, so that I'll start something. So The remaining time, let me discuss about something else. So let's actually quickly summarize our two-stage Miller OTA. So here, what is my omega u? Gm1 by Cc. What is the second pole location approximately?
GM2 by CL.
Gm2 by Cl prime. Okay. And for a good phase margin, what do you have to do? Omega u must be much smaller than P2. That much is fine. And depending on how small it is, the phase margin will also be equally higher. Okay. So now let's try to understand this condition from a different perspective. Now let us say I take only the second stage here. So let me draw the second stage alone. I have Gm2. I have at the output Gl prime and Cl prime. Okay. Now let us say if I consider only this stage, what will be the omega u for this? Only this guy, what do you think will be the omega u? Okay, this is a first order system or a second order system? First order. For a first order system, what is the omega u? Huh? DC gain times the first pole.
Yes.
What is the DC gain here?
GL by GL.
Gl prime. What is the pole location?
GL by CL.
It is Gl prime by Cl prime, right? Again, for finding pole, you are going to assume input is not there, so which means this is not playing any role. So you just have this RC. Okay. So what is omega u now? Gm2 by Cl prime. So the point I am getting at is the second pole we have in the two-stage Miller OTA is basically the same as the omega u for the second stage alone. Okay. So what I'll write is P2 is basically omega u for the inner stage. Is that okay? By inner stage, I mean this guy. This is the inner stage. And our actual omega u, I'll call it as the omega u for the outer stage. For the outermost stuff, omega u is Gm1 by Cc. And for the innermost stage, omega u is Gm2 by Cl prime. Okay? And for a good phase margin, we know this is the condition. So I can write it like this. Omega u outer must be smaller than the omega u for the inner stage. I'm just rephrasing the same known stability condition in terms of omega u's for different stages. That's all. Is that okay? Okay, so let's have that in mind. So for stability, we need to make sure the omega u for the outer stages must be smaller than omega u for the inner stage. Okay? Cool. So let's say I have this two-stage OTA and I find that the DC gain is not enough. I want to increase the DC gain, but let's say I don't want to do cascade because of swing limits and stuff. So what can you do? Huh? Sorry? No, okay. I have this two-stage OTA. It's having some DC gain. I'm finding for my application this DC gain is not enough. So what can I do to increase the DC gain? Yeah, you can cascade one more stage. I mean, here to get a higher DC gain, I cascaded 2 stages. I can go and put one more stage and increase the gain, right? So that will basically give rise to a 3-stage OTA. Something like this. But now here you will have, okay. Yeah, here again you will have the stability problem, and here it will be even more pronounced because you have 3 capacitors. So again, to stabilize it, you have to do some kind of compensation. And you can use Miller compensation for our help. And there are a couple of ways in which we can do Miller compensation here. And one way to arrive at a 3-stage Miller compensated OTA is by following. Say you have a 2-stage OTA. So this is something we know. I'll not show the zero cancelling resistor for simplicity. You can add it. So this is my 2-stage OTA. So to get a 3-stage OTA, what can I do to this? Okay, I'll probably lead you there. See, this is a 2-stage OTA. It's well compensated. It is stable. Now to get a 3-stage OTA, one thing I can do is I can replace the second stage by another 2-stage OTA. It is like inception, right? OTA within OTA. So the deal is you replace now second stage by another 2-stage Miller OTA. So if you do that, the circuit will look like this. This is my first stage. So I have the CC that will be put around the second stage, and the second stage itself is now a 2-stage OTA. That's all. I'll just show the load cap alone. So let's say this is now GM2 and GM3. Okay. And I'll call this CC1 and let's say this is CC2. Right? So now if I include all the conductances here, G1, let's say this is G2 and this is some GL prime. The DC gain is obviously the product of the individual DC gains, GM1 by G1 times GM2 by G2 times GM3 by GL prime. You get high DC gain. Now again we need to find the conditions for stability, right? And for that I'll use the understanding we had here. For Miller OTA, the stability condition was make sure that the omega u for the outer stage is smaller than the omega u for the inner stage.
The state means the whole state.
Whole stage, yeah. So here, what if this is the outermost stuff? What is the omega u for the outermost thing? Again, assume that this is basically another OTA, right? This is we derived it using a 2-stage OTA.
GM1 by C.
For the outermost stage, omega u is what? GM1 by CC. CC1.
1.
Okay. I mean, because you assume that this guy is another OTA, and you can think of it as a 2-stage op amp, so that omega u is GM1 by CC1. Now this must be smaller than the inner stage, and the inner stage we have now is this guy.
GM2 by CC.
So this is the inner stage itself is a 2-stage OTA, and what is the omega u for that?
GM2 by CC.
GM2 by CC2. Make sense? So let omega u1, this is let's say omega u2 is GM2 by CC2, and we do have one more inner stage which is this guy. What is the omega u for this guy?
GM3 by CL prime.
GM3 by CL prime, right? And this is equal to. And again, for stability, we know that the outermost omega u, which is this guy, must be smaller than the omega u for the inner stage, which is CC2, which in turn must be smaller than the make sense? So you make sure that the outer loop is operating at a, it has a lower omega u than the inner loops. So So this is the condition you need to ensure to get a stable 3-stage OTA. And I mean, now we can, you don't have to stop, you can go for 4-stage also. To a first order, it will not. See, again, the expressions I have given are all approximate, right? See, only thing exact here is the omega u for the third stage. Because if you consider only this guy, it is a first order system. I can exactly write the omega u. But for all others, these are just approximate expressions. Okay. So now, I mean, let me just quickly show a 4-stage. And again, logic is the same. You can start with a 2-stage OTA. Now the second stage will be a 3-stage OTA. So this is the second stage now. I can think of this as the second stage. We'll probably relabel these guys. So I'll put something for the first stage here. Okay, that's all. So this will be CC1, CC2, CC3. Again, for stability, we have the same old stuff. What is the outermost omega u here?
GM4 by CC1.
No, outermost GM1 by CC1. This must be smaller than the omega u for the inner stage,
GM2 by CC2.
which is GM2 by CC2, which in turn must be smaller than this, which in turn must be smaller than this. And practice 2-stage and 3-stage OTS are very common. 4-stage you will rarely see, and beyond that, I mean, no one has seen. Because by the time you get 3-stage, you can actually get gains close to 1 million. So beyond that, there is no other point, right? Because you see that as you keep increasing the number of stages, your overall omega u is also reducing. This is your final omega u for the entire system, and you see it's much smaller than the other stuff. So yeah, okay. And okay, I forgot to give name for this. Whenever you come up with something, first thing is give names. So this technique is called nested Miller compensation. And I mean, this is not the only way in which you can get a multi-stage OTA. As I mentioned, the thought process we took was we kept replacing the second stage in a 2-stage OTA by higher order stages. There are also a couple of other techniques in which Miller compensation can be done. If you are interested, you can read it up. We have something called reverse nested Miller compensation. I will not explain it, but you can read up if you are interested. Cool. So that kind of ends the discussion on Miller compensation. Now, when we started off with stabilizing higher order systems, we came up with 2 techniques, if you remember, right? So we initially started off by saying that we wanted the closed loop poles on the real axis. For the open loop system, we will have something like this, and the root locus was doing this. We wanted to make sure for a large DC gain, the closed loop poles lie on real axis, and one way we can ensure it was to keep them far apart initially, so that for a large range of gain, it is lying on the real axis, and that was Miller compensation. We also thought of we also came up with one other technique. Remember that? Feed forward, and the idea was basically you introduce a 0 here, so that the root locus kind of does this, right? So this is another way in which you can keep the closed loop poles on the real axis. You introduce a left half plane 0, and that is called feed forward. And if you guys had not realized it by this time, the 5th question was indeed a feed forward compensation. The 5th question in your exam That was basically something like this, right? I didn't give the conductances, I just gave capacitances for simplicity. So this is your two stage, and I also gave another stuff like this. So now again you see you have two paths, right, for the input. If this is the input and this is the output, there are two parts existing from the input to the output. So what will be present now? A 0 will be present, and that's basically this, right? We actually wanted an LHP 0 here to make the system stable, and this is exactly doing that. So we'll start with this and continue in the next class.